Can you hear me? Hello? Can you hear me?
Yes, sir. Yes,
Can you
sir.
Yes, sir.
please see the screen?
Yes, sir.
Yes, sir.
Okay. Start. Okay, let me start connectedness. I have given all the notes. No more notes will be there. This is the last chapter of this semester. Here I forget. The syllabus for major will be actually the whole thing. The whole semester. But emphasis should be given emphasis after minor chapters. Why I am saying this? Because you need many concepts from before minor. So don't complain that but here you should compactness, function space. Under function space will come Ascoli-Archila theorem, particularly Archila theorem, Dennis theorem, and Stone-Weierstrass theorem. And this connectedness. The last 2 minutes I have uploaded. Okay. This is the emphasis. Basically, here in some problems you may need to use your old knowledge, like first countable things. And here compactness, I mean all sorts of compactness. Whatever I taught. That is particularly compact, countably compact, Lindelof. And then something you should look at the definition, sequential compactness. Okay. I have defined pseudo compactness also. Now let me go this to connectedness. Look, last semester I defined connected metric space. But in the definition, in the working, there is not much difference between connected metric space and connected topological spaces. So whatever motivation I gave last semester, that is valid here. Connectedness basically intuitively means one piece as a space. We often say that connected space. We don't need to bother about mentioning topological. Connected space means connected topological space. One space, basically. So definition, it will be same thing. Basically, idea is that you have a topological space and you know already x and phi are both open and closed. When you have both open and closed, that is also called closed-open sets. Okay, question is that does there exist a subset of X such that is neither empty nor whole thing but is closed? That means a third closed-open set. Okay, that is the question. Why it is integrated piece? Now look, if you have third closed-open set, then you will get another one, x minus c. That will be also closed-open. Since a not equal to x, so this will be not equal to phi. And since a not equal to phi, so this will be not equal to x. So this will have the same behavior. That means if you have third closed-open set, then you will have fourth closed-open set. And consequently, look, here x can be split into like this. And many of the things we can do always open sets. They are both open, they are disjoint. And many things we can do on A and this. And that means two different pieces. They are two different pieces. Okay, right. So that is the thing is that one piece. That means connected means I should not have this. I should not have this. So that exactly the definition that I say that called connected whenever phi and x are the only subsets of x, they are simultaneously open and closed. Okay. Now, so that I say this is connected. If x and phi are the only open sets in X2. Now look, study of connectedness actually is a bit more problematic than compactness, because here compactness you got absoluteness. Absoluteness. What does it mean? If you have x star logical space A subset of X, and we have found that A is compact in X star with respect to the topology on of X, if and only A tau way. This is compact. This is subspace topology. But for connectedness, we do not have that. So that if you have, suppose you have this here, y, I have taken y. If I say connected subset, what I mean that connected subset. Here I said that. What do I mean by connected subset of X? It means this. The X may not be connected. This is connected. For connectedness, you will have to go to the its topology, relative topology. Okay, there is no way to link that. Okay. Y tau y is connected. This, not y with respect to this topology. Okay. That means open sets I am taking the splitting, that will have to open with respect to this trivial topology. Okay. So be careful about this definition, connected subset. To some extent we can overcome this difficulty by considering functions. Okay. So now next thing that I taught you last semester, so that first theorem 1, if they see that I have proved last semester for the matrix piece. So we have given equivalent conditions that helps according to your situation. That means, look, if you have open sets, so that if you have this A is open, so this is also open. So that if you have this X, suppose UV open disjoint, then UV, because of V is X minus U, so V will be closed. Similarly, U is also closed. So that if you can split into two open sets, disjoint open set, you can split into two disjoint closed sets. That is the condition B and C. Okay, B and C. But the important thing is that D, you should look at that. Any two functions, any functions equivalent to that. Often we, while dealing with connectedness, we use D. D is saying what? That whenever you have a function, with 2 points, it is called 2-point space. 0 and just notations, you could take anything, only 2 points you need. With discrete metric, that means T01 is, you can take 1 and otherwise it's 0. Okay, that means it will give you the discrete topology. Discrete topology. Basically, you need to say that it has got the discrete topology. Then any X tau will be connected. You can prove very straight. If and only if, whenever this is continuous, the discrete topology here implies F is constant. That means whole thing will go to 0 or whole thing will go to 1. In probability, you have got the so-called indicator function, or major theory they call it characteristic functions. So this will be that thing. It will be a characteristic functions. So that basically you can say that it will be a characteristic functions on the proper subset. That means if is constant, that is F is either this It is, it is either chi A I am writing, or else f is chi P, where hmm, where A equal to this. Let me explain that. That means, that means either you have fx equal to 0 for all x belongs to x. Okay, right? That means this is will be chi of this one. That means fx equal to 1 is empty. That means this is chi of empty set. Okay, and or else fx equal to 1 for all x belongs to x. Means chi x. Okay, that basically integrated function you get that. F will be constant. This is very useful. I left an exercise that you can prove straight. That is not difficult. It's not difficult. But the thing is, I mentioned something. Every proper non-empty subset of X has non-empty boundary. Okay, remember that if you have topological space X star, if you have a subset of X, the boundary of A, this is called the boundary of A, or frontier of A, is defined as saying every non-empty subset has non-empty boundary. Non-empty subset has non-empty boundary. Because if you have empty boundary, then it will be disconnected. That you can prove that. Okay. This is actually topology is used, but often it is this fact is used in function analysis. This fact for connected. Okay. This you can prove. Okay. Now the preservation by that connectedness should be sort of topological property that should be preserved by homeomorphism. Next theorem actually says connectedness is preserved by continuity. Connectedness is preserved by continuity. That means if you have a continuous map between two topological spaces, and suppose here A is connected in X, that means A tau A is connected. This says that implies if A sigma Fa subspace topology is connected. So in particular, if you have this, if X tau is connected, then this will be connected. That means we say that continuous image is a surjection, so it will give you image, continuous image, a continuous image of a connected space is connected. Okay, so particularly connectedness is a topological property. That means preserved by homeomorphism. Homeomorphism is much more than continuous image. Because homeomorphism is in one-to-one correspondence. It is continuous, its inverse is continuous. It's a topological property. That is preserved by homeomorphism. Let me give nice examples of application of this result. Okay. You will have in-class exam, so you won't have access to anything. It will be closed book everything. So that horse particularly don't have the advantage of turning over the pages of that. Okay. So look here. I have given in theorem 3, look. And this is giving the example of before that. Theorem 3 I am not proving. This I have proved last semester. That if you take usual distance matrix, that means it will give you the usual topology, then the subset A is connected if and only if A is an interval. In now you see that if I ask you this, that there can be any homeomorphism, of course with respect to the usual distance. Now look, if I give you this, then it says there won't be homeomorphism because this is compact, this is not compact. Compactness is a topological property. But here none of them is compact. So you can't use that. Okay. But I can use connectedness. By using connectedness, I can show this is not connected. Now look, if you have homeomorphism, before that remember why I gave that question in minor. Minor I have given on a point, but in general, suppose you have homeomorphism. Don't forget it. Homeomorphism. In general, you can prove that. You can look at your arguments, what you have used. Suppose phi equal to x. Then you'll have this restricted function a to tau. Actually, not that. I will do something else. F x minus tau x minus. It is a one-to-one correspondence, so it will image will be fx minus fa. That means y minus fa. If you delete a here, you will delete fa, and correspondingly sigma this. This is a homeomorphism. If you think this is because restricted map, because this will be one-to-one correspondence. Since this is continuous, its restriction here will be also continuous, and same way from the other side. Look, f inverse from here to here is continuous, so f inverse restricted to will be continuous. So it is a homeomorphism. Okay, this is a homeomorphism. Now you see that why these two cannot be connected. So I will use this. Use this. So make sure that you understand that minor example result. So that suppose, if possible, suppose is a homeomorphism. Now look, f1 will be here, but it is an open interval. So that f1 will be somewhere here, something here. That means 0, 1, if you subtract 1, that means you will get a function restricted to this. 0, 1, 2, you will have this thing. Just write this function. Of course, you will have the corresponding subspace topology. That will again be given by the usual distance function. Now look, here, this is connected. Is it still an interval? Look at the trick. But this is not interval because two pieces you are getting, not an interval. So this is not connected. So not connected. I am using this result in both ways, not connected. So that means here you are getting connected and not connected. But connected is a topological property, so you are not getting homomorphism. So if you had homomorphism, you are supposed to get a homomorphism here, but you can't homomorphism. So this is not homomorphism, no homomorphism. Okay, this way, this result you can, this trick you can use in many other things, like, well, look here. Remember that 0, 1 to S1. We have basically taken this function like this, but that you'll have to wait for a while, but let me tell you, still you can do that. That this one you got quotient space. Okay, remember that. How did you get that? So there will be a continuous function, but it cannot be homeomorphic. No homeomorphism there. Reason is same thing. Look, here you have this circle. Okay, now here I will do the different technique. That half. If you omit half, this won't remain connected. But wherever f goes, half goes. I'm saying no homomorphism. I'm saying there is a continuous map called quotient topology is there, but no homomorphism. So that you'll have to start with an arbitrary f if possible. But wherever is that f half, it will be pieces, not two pieces, one piece. Look, still only. So this will be still connected. Though how will you prove it? It can be proved later on. We'll talk about path connectedness. By path connectedness, it can be proved. It will remain path connected, so it will be connected. So here again, you can't have a homomorphism. This is the way you can do it. Okay. Remember last semester I did this thing. I gave circle. Sorry, straight line first. X plus y equal to 1. Then I gave the circle. And then I had this. This 4. I asked, find out which pair is homeomorphic, for which pair there is homeomorphism. Look, 1 and 2 cannot be homomorphic because this is compact, this is not compact. Heinball theorem, this is closed but not bounded. But this is closed and bounded, this is compact. So 1 and 2, they can't be homomorphic. Now 1 and 3, 1 and 3. Look, this is this hyperbola, not the whole thing. This is disconnected, but this is connected. So 1 and 3 is not homomorphic. Similarly, 1 and 4 is not homomorphic. They are not homomorphic. Okay, because this is disconnected, this is connected. Now 2 and 4. Again, the look, you can see this is compact, this is not compact. Okay, Or also you could use connectedness also. Okay, 2 and 3, they are not homeomorph. Similarly, 2 and 4, because 3 and 4 is the same argument you take them. This is compact, this is not compact. So it's not homeomorph. Or you could use connectedness. But these two only, 3 and 4, are homeomorph. Because this is just a change of the coordinate system. Are homeomorph. Here I have used both connectedness and fact. Both connectedness and compactness are topological properties. Okay. Right. Here, I just want to mention. Suppose you have a Tychonoff space. These are actually all problems we learned. Tychonoff space and having more than one point. Now assume additionally this is connected. Then cardinality of x will be greater than equal to c. That c is the cardinality of the real line. That means it will be really big. It will be uncountably infinite. Now look, I am giving you Tychonoff having more than one point and connected. Then it has to be really big. How to prove it? Look, since Tychonoff, remember that. It means what? Particularly completely regular. Completely regular. So that you have more than 2 points, more than 1 point, so that you have 2 points here. So that because of this, I will get a function x tau to take 0, 1. Such that continuous function. Okay. You take in R also. That's not a problem. Okay. That fx equal to 0 and fy equal to 1. You could argue with this also. It's not a problem. Okay. Right. Now look. So you get this. This is 2 points is required. Now, if you have this, now x tau is connected. So fx is connected. So fx is connected in there, which is connected subset of R. So that means fx is an interval. Now look, fx is an interval, it is contained in this. But what is the meaning of that interval? But 0 and 1 is here. Okay, so if it is an interval, that means this is this. Because 0 and 1 is here. So that interval means in between all the points will have to be there. So it is there. And this is there because it's the range is there. So that fx you are getting cardinality is C. Okay. Now where is C? Fx. Now look, we have got the result. When you go, cardinality can only decrease, not increase. So that's the function for any. The cardinality of fx is less than equal to cardinality of x. You see why I am writing greater. Cardinality of fx is coming C. Got it? So that if it is Tychonoff plus connected, so it will have this. For metric space is the Tychonoff. So metric space you could prove directly, not the reference of the functions, metric space. That means usually some exams they give this. So if you have a metric space, having more than one point, that is, you have 2 points, then you can have this function. What is this function? You remember when you have a two sets, non-empty sets, the metric space, then you have this function. Closed sets, disjoint. Closed sets, disjoint. TXA, TXA, TXP. Right? So A you take this, B you take this. Be careful about this. So FJ, this is going to 0, 1, this function. Define FJ. Because here I am taking XY. So this is TXZ, TXZ plus DYZ. This is continuous. Okay, this is lying in between 0 and 1. Same arguments are now being applied to show that we have this. Okay. Actually, many places they don't teach topology. They only teach metric space. I mean, IIT Kanpur teaches only metric space, not topology. But I do not think that's a proper thing. But then there are many things where I told you the non-materializable spaces. So that's why when for some admission test, entry test, even for TI for ISL, they often give the questions, formulate question only in terms of metric space, so that students they don't have the disadvantage. So for metric space particularly, you can go through this function to prove that result. Okay, right? So I have given you a problem. So that the intermediate value theorem that I already mentioned, intermediate value theorem, you should look at the comments. Yes. Intermediate value property says that a continuous image of an interval is again an interval. That's the thing. That means now suppose you have a like undergraduate, you have a function from the interval. To take open interval, close interval, not open, not close. I'm just doesn't affect on the arguments of that. In fact, I can take real valued functions. To take system interval. An interval's proper definition. How do you define interval? Okay, let me tell you the definition again. That you need polygonal connectedness. Okay, so that what is the actual definition? I is interval. I is called interval if whenever if for all xy belongs to y and 0 less than t less than equal to 1. Look what I'm doing. This 1 minus tx. Actually, if you take t equal to 1, you will get t equal to 1, t equal to 0. If you take t equal to 0, here you will get x, and t equal to 1, you will get y. Okay, actually, this is called a path line segment. A line segment from x to y. If you change t here, 1 by t here, that will be a line segment from y to x, 0 to 1. At 0 you are getting x, at 1 you are getting y. So it's the line segment from x to y. And it is often denoted to standard notation like this. It can be defined any linear space. So this actually is defined like this. Function analysis is very important concept. It's called a line segment. Called the line segment. Getting the directions also from x to y. So interval, you can say that interval, if every line segment joining 2 points in I again lies in E. Okay, so that means you can write in other way that for all xy belongs to I, this line segment is subset of. This is called an interval. Okay, this is interval. It is also defined in any linear space also this way. Okay, right. But you will say this I can define for convexity. Usually you can do because convex definition is that. Okay, so that here, suppose in interval, so in R. So by this result, what I have not given the proof. I proved last semester, but if you look at the proof, it's an interval, so it is connected. So this is connected in R. But a connected subset is an interval, so it is interval. In fact, that result, a subset of what is connected, if and only if it's an interval, I am using both ways. Here, look, I have an interval, then I am using this is connected. Then continuous image of a connected series is connected, so it's an interval. The other way I am using. So, image of an interval is an interval. Okay. Now look, if you have this, I equal to particularly this, then you know this will be an interval already, but it is compact. So it will be compact also. That means it will be closed and bounded. That means altogether it will be closed bounded interval. Closed bounded interval will look like this. That means if you have a continuous function, its image will be always like that. Similar type of interval. But other intervals you may not have that. Okay. Like simplest example I am giving you. Like, look here. Take, this is a continuous function. Here so bounded interval. Okay, because it's not closed, neither closed nor open. And what will be the interval here? Here it is going. So, okay, look here. It is coming unbounded interval. Here it is bounded interval. If you take this open, then it will be open, but it will be unbounded interval. So that only for if you take this kind of interval, I know it will have a similar type of interval. But otherwise, you can have some other functions too. You can construct other type of functions to show the examples for the other things. That only for this is guaranteed. So that you should do it. Okay. I'm going to take a break of 5 minutes. I will come back. Probably Monday I won't take the class. So tomorrow I will take the course. But exercise 1 and 2 that I talked last time. Exercise 2, the number theory they use it often. But if you ask a number theorist how do they prove it, often they won't be able to prove it. They think it is known, well known. Okay. So make sure that exercises 1 and 2 you do it yourself. Okay. Right, I have talked about that. Now I will start path connectedness. That more on connectedness, I told you that. Okay. I will talk little bit on that. I want to finish as soon as possible. Monday I won't take the class, but Tuesday I will take the class. Tomorrow I will take the class. And if it is not required, then next Friday I won't take the class. Okay, so I am coming back. Okay, I want to teach you path connectedness. So that I have given a result of that. Okay, right. But before that, I want to teach you something more on connectedness. Okay, that will come later on. That. But connectedness, the first thing I proved that if you have this A, that means A tau A is connected. Then if you have any set here between, then B is also connected. That means B tau B is connected. If you go for all these topologies, you will have so tau A, tau B will have to consider. But if you go by that functional characterization of the connectedness, it will be easier. Here, I should tell you that in the end you should write, I didn't write it properly in the sense that fx equal to 0 or fx equal to 1, but x was chosen arbitrarily from B. That means for all x and B it will be either fx, that means what I should wait. What I should tell you that, look, let me prove that, how I proved this. Okay. I said, look, you have x tau. It is not connected, but you have A tau is connected. This is your hypothesis. And you have a set lying in between this. It may be whole in a bar also. This is hypothesis. And then conclusion. I didn't go through the subspaces on that because that would be tricky, inconvenient. I went for functional characterization of connectedness. So you take a function. Since it is not matrix space, I have taken the net so that I'll have to show that any continuous function is constant. That means everything will go to 0 or 1. Okay, so that here I consider this function restricted to this. Remember, tau A is same as okay. So this function from A tau A to 0 1 is constant. Now Ax belongs to B implies X belongs to A bar. It not be a metric space. So implies there exists a net x lambda in A such that x lambda converges to x. For continuous functions, so that look here, f is continuous here, whole thing here. Okay, so I can apply. I am applying f here. So fx lambda goes to fx. Now this fx lambda is coming from A. So you can split it into two cases. Suppose fx equal to, I think it would be better to write that fx equal to 0 for all x, suppose. Then fx, so don't confuse that, fx prime. Then this is 0, so fx is 0. But x was chosen arbitrarily from B, so that fx equal to 0 for all x belongs to B. I think you should split into that. It is not written wrong, it is not written properly, it is confusing. Because you may think for one point it may be 0, another point it may be 1, the way I've written, but it was not like that. And case 2 is suppose fx equal to 1, fx prime equal to 1 for all x prime 1, then it will be 1 for this. But that means it is constant, so it is connected. Okay, that in particular closure of a connected space is connected. Closure of a connected space is connected. Okay, so that you should do that. Closure of a connected subset. In the proof, we do two cases, that either you assume fx equal to 0 for all x in A, or fx equal to a 1 for all x belongs to. Then both cases you will get the similar thing for B. That's the better way to do it. The closure of a connected subset is again connected. It's a powerful result actually. Okay. Now the thing is that this you need actually. I to God R is connected, fine. But how will I prove this? This is connected. Where n greater than. How do I prove that? Okay, you will see that, how to do that. One way you can prove it is path connected, but then I'll have to go to the path connected. Without going to the definition of path connected, just by using the definition of connected is how to prove it. So here, that first section I am proving, looking at the study of unions and intersections of connected subsets in a topological series. That means, but I said we would like to examine. That means suppose you have this, and suppose xi. It's a family of subsets of the family of connected subsets. Then the question is whether this will be connected, their union and intersection. If of course if it is empty, non-empty, because empty set connectors we don't define, they are connected or not. Look, this one you can immediately say no, it did not be true. Look, in the real line, if I take this, this is connected, but their union is not connected because it's not an interval. So union did not be connected. Okay, but we will say intersection will be connected if it is not empty, because that will be an interval. Okay, that is fine. So intersection, if it is not empty, then here you see that it will be connected. So Indian would like to do that. Okay, now we will look that I have given the definition. Usually the books do not do that. I have done that. They give you a result on that related to that, but they don't define this the way I have defined. Rarely you find in a book like this. Chain. That means chain means consecutively you are going and there they have non-empty intersection. Problem is here you do not have the non-empty intersection. Now look, if the interval, if I go like this, here you see that if you take interval, whatever it is, suppose one I1 interval, I2, suppose I3. But suppose I1 intersection I2 is non-empty, and I2 intersection I3 is non-empty. Then what will happen? Okay, so then it will be again an interval in real life. Okay, but that means here is the idea of the chain. You're going to the next one with non-empty intersection. That's the idea of chain. From I1 to I3 you are going this thing. So that here For chain to define chain of subset, I don't need topology. These are basically set theory. You can use in computer science also. So that here I am saying the chain. Look, what I have given the definition of chain. So X you have a set and Xi is non-empty family. That means I is non-empty and each Xi is non-empty. Non-empty family of non-empty sets for all I belongs to I. Then I say this is chain, that any two sets can be constructed by like this. I can go through a chain. That means if you take two sets here, suppose, given xi, suppose you have two sets, xi, xg. Okay. I'm not saying their intersection will be on MD like this. I'm saying I can pass through, like I will have a chain means finitely many collections of sets. X, I1, I, K. Okay. Such that xi will be equal to the first one, xi1. And this is xik, fine. And also consecutively that the intersection is non-empty. That means x, look what I have given, x I l minus 1 intersection x I l non-empty for l belongs to 3. Here I am taking k because starting from 2, so because 2 minus 1, that is I1 will come. So that means with the next one, only thing I am putting that, I am not saying, be careful, I am not saying this one and this one has non-empty intersection. I am not saying this one and third one has non-empty intersection. I am with the next one, it has non-empty intersection. With the next one, that means this one has non-empty intersection with this one has non-empty intersection with this. Look here, like this. Look here, 1, this x1, this x2, this is x3. Look, here it's a chain, but x1 intersection x3 is empty. So be careful. Only the next one. I have the intersection here. Next one. So this is a chain. Here it's a chain. That's the idea. That means in the connectedness, if you have a chained collection of connected subsets, then this is also connected. The idea is same. Like way I said, the functional characterization of connectedness. I am using it. I am using functional characterization of connectedness. You can prove that. This way you prove that each xi, the function will be constant. But look, I have taken trouble to that. That means I am saying you are having a topological space, we are having a chain. And each xi is connected. That means xi, tau xi is connected. That means chain of connected subsets in that chain. Then this is connected. Now look here, what I prove. Proof is very simple. Here I am taking a function. This two-point space, discrete space. But then when you restrict to this each xi, it will be constant. But now you'll have to show that because this is connected. I'm using functional characterization of connectedness. This is connected. But you may say on fxi, look what is the idea I'm doing the chain. Fxi and fxj, you say here it is 0, it is 1. I'm saying it is not possible because of the chain. Look here, if you have chain, now look, why it is not possible? Look here, you have xi. Here you are going this way. Take suppose. Now look, if you have everything 0 here, then here it is also 0 here, including this part. That means this will be 0 here because all of them it is constant. Similarly, it will be 0 here. So you don't have this possibility. You'll have to argue the chain that it has to be, if it is 0 here, it has to be 0 here because it's a chain. You see if you draw the picture, it will be immediate that since this for this part, if it is 0 here, so it is 0 here and it is constant here. So that means it will be the whole thing, it is 0 here. That means it will be 0 here. Similarly, it will be 0 here. So that it cannot be 1 here. So that's the argument I have used. The idea is very simple. So that if you have a chain of connected subsets, its union will be connected. So that I will just prove this much today. That this much connected components I will do tomorrow. But now look, corollary 3, special case of that. Okay. What is corollary 3? That I'm saying if this is whole intersection is non-empty, then obviously you will have this for any chain. In fact, then for the chain you can take only any two sets. If you have two sets and 10 chain, you see that non-empty family of connectors, then image xi is chained because this. For any two sets, I think only two set chain I need. Okay, it is itself a chain from xi to xj. So chain means I need a set chain of sets from xi to xj. That I told you. Intersection of two consecutive sets will be non-empty, but here itself it is, so it's a chain. Okay, now, well, got it. Now look, its application is look first the corollary 3. Now Rn, say how to prove this is connected. Well, now look, Rn r square you just look. Rn line also can be defined the same way. Okay, so the r square you look at to take all the lines passing through the origin. Okay, all the lines passing through the origin. So their intersection is non-empty because the origin is there. So their union will be connected, but union is the whole Rn. That's it. Line in the n dimension, higher dimension, it can be defined similarly. Okay, you should know define line in Rn. You know for n equal to 3 also you know the line, how to define line in RQ. Same way you can define. You have to see that how to define that in terms of the parameters you can define. So if you take all lines passing through the origin, then you apply corollary 3, that will tell you this is connected. Okay, got it? That's the idea, advantage. Okay. Now look, corollary 4. This is a special case again of that. I'm saying yes. Suppose you have, this is a bit tricky, that suppose for each pair of points, you have a subset of x which is connected in x. I will give you problem in the major exam on connectedness. I only plan to give you, okay, let me tell you, 8 or 9 problems, but let me tell you, your exam in the April 6th that I've looked, starting from 8:15, 10:15. But I will give you extra time because there is no next exam there. But first, let me tell you that you won't get the answer script first. You'll first get the question paper. And I will give you additional 10 minutes for that. For first 10 minutes, you will read your question. Only after that, you will be given the answer scripts to write. Okay. So first 10 minutes, You will have time to read the question. And then you will start writing. Before that, I won't give you the paper to write. Okay. And this can continue. There is no problem with the other class 11 a.m. and that. Depends on that. But I think 10 minutes here, 10:25, another 15, 10:40, so I will give, I think. Okay. But it can, but that I will see that after setting up the paper, that how much time you need at that. Okay. So I will give probably 8, 9 questions, not too many questions. But for connectedness, the minimum 2 questions I will give. Now suppose you have this, then X is connected. Idea is very simple. You pick up a point A and keep it fixed. So you get this for any X. Now pick up any X belongs to X. So this is connected by hypothesis and its intersection. So here the index set is actually X. Index set is I is X. So X belongs to X is at least non-empty because it A is here. This is non-empty. So that union of this will be connected because each of them is connected and their intersection is non-empty. But this is X. So X is connected. Okay. Right. Anyway, the previous thing, how to show that this is connected. Look, each such line is the homeomorphic image of this. That you should argue. Each line is the homeomorphic image of this real line. So that is why it is connected. Okay, particularly a continuous image of this. Okay. So that here this is also a chain on that already 5. It is only that you are taking the countable collections of them. But each action is connected and to consecutive ones. That is this. How to prove that clearly Xn is a chained collection than that? Because any two you take, okay. Why it will be clearly I said it's chained collection. Well, look, if you take any this, why it will be a chained collection in that connected subsets. I am giving that only two consecutive one is this. So suppose xi, xk. Then I can get a chain that because xi plus 1, I'll go this way. Xk minus 1 to xk. But two consecutive ones, that is the idea of the chain. This is non-empty intersection. Similar, this is non-empty, this is non-empty. So this is a chain. Okay, so it's a chain collection. Now that example I have given that. Okay. Got it? So I will teach you connected component later on. Connected component means, I'm just telling you what is connected component means. I'm not saying that. What is connected component means? Suppose X tau need not be connected. Suppose there exists a connected subset. Suppose, does there exist connected such that if I have this and B tau B is connected, then B equal to A. That means regarding connectedness, this is sort of maximally connected. Maximally connected. Does there exist? That is the code. The maximal connected set, if it exists, is called a connected component. So I will teach you tomorrow on these things. Okay. Right? So that connected components I will teach. Again, the path connectedness, I'm not going to teach it today. Tomorrow I'll teach. But path connectedness, some of you may be interested in algebraic topology. I would like to mention that here I just want to give you some information. Path connectedness, you will see that it is actually in Monkray's, I think, in Willard you will see a chapter on homotopy theory, path connectedness. Path connectedness is related to homotopy theory. Okay, Monkray's you have more details than Willard. And now let me tell you, algebraic topology studies topological problems with the help of algebra. Because it is called topology. But it has actually two branches apparently. Homotopy theory and homology theory. But look, basically it is the same thing. Here this path connectedness is related to homotopy theory. So that if you are interested in algebraic topology, you should read path connectedness carefully, and then from Monkray's and Willard you should read. That is the basic thing. Now homotopy theory, you use more topology, less algebra. Homology theory basically same problems you deal. You use more algebra, less topology. This is also called homological algebra. But let me tell you that algebraic topology, many people think of that. Basically, it is also oversaturated field. But that's why people are going. But in algebraic topology, like other areas, has got nice applications. Now, one area is that people are working. It is called topological data analysis. TDA. This is here in many problems they actually deal with problems coming from algebraic topology. Deals with algebraic topology. So topological data analysis, usually they hire postdoc, but then some universities they also encourage for PhD. So if you are interested in topology, but that application, you can think of this area, topological data analysis. But before that, you need to know basic algebraic topology well, so that you need to homotopy theory. You can look there either in Monkray's or Willard. In fact, homotopy theory, the basic first technique that I said that path, how to get a product of path. In page 10, you'll get a proposition that I said the product of paths. Okay, so I will talk tomorrow on that I am giving you the information on that. This you want to go to the application side. Okay, right, see you tomorrow. I will take again class same time. Okay, see you, bye.